Hi everyone, welcome back to VLSI for All. I'm Apurva Dixit, today's host, and we're honored to invite our guest Steve Hoover, who is the founder of Redwood EDA. Before we start our podcast, I would like to ask you the most important question. How has been your journey in India so far?
Oh, India's been wonderful to me so far.
Okay.
Everybody's been really inviting, and it's been a long journey. I'm tired. I don't know how smart it is to do a podcast when you're jet lagged, but you know, the airplane, not the most exciting experience, but being in India has been great.
Okay. What all places have you covered until now?
I have a long lineup of talks and visits. This is my first time in India. It's my first time in Asia, in fact.
Oh, okay.
And I work with a lot of folks in India.
Okay.
So yesterday I was able to meet with 5 students that I've worked with in the past for several years. And finally, we were able to meet in person, all sit down to lunch together. It was really nice.
Okay. So you have not covered like the monuments, and you have not actually gone into touristic
I have no
places.
time, unfortunately, for pleasure.
Okay.
But you know, just seeing the sights along the way is
Okay.
a real nice
So
experience.
before we start into the technical questions, our audience would like to know a bit more about you. So we'll start with the introduction from your part and about your company. What do you do?
Well, so my background is circuit design. That was most of my career. And throughout that career, I started to realize, you know, opportunities for doing things a better way.
Mm.
And I realized after enough time that I wasn't really looking forward necessarily to going to work in the morning anymore.
Mm.
I really felt like I could have a deeper contribution to the world by improving the methodology for designing circuits for the career that I had, make that a more pleasurable experience for other engineers. And I felt more passion toward that. And so I essentially one day stood up and walked out the door and started Redwood EDA so I could focus on those challenges. So I sort of look at my the first part of my career with big companies working on large-scale integrated circuit design as field research for what I'm doing now, which I feel is something that can have a greater impact to the you know, silicon community.
Okay. So what inspired you to leave a stable career in logic design and verification you have been doing, right? So why did you leave it? Like, were you bored out of your job, or what motivated you?
Stupidity, perhaps.
Okay.
No, I mean, it's just that. It's the wanting to do something that I feel passionate about.
Okay.
And you know, having almost 20 years in the industry, I feel like I have a lot of awareness of the ecosystem. It's a very sophisticated ecosystem and complex. And a lot of the innovation, you know, naturally happens out of academia, and that, in theory, trickles into the industry to have impact. But such a large industry and large ecosystem, it's very difficult for academia to participate in an ecosystem like that. And so it's becoming harder and harder for academics to have the impact that mechanism is intended for. And I feel like all that experience I've had in the industry gives me a good perspective on the industry to understand all of the pragmatic difficulties of making a real impact. And, you know, I've been at this for a decade now with Redwood.
Okay.
I still would openly say I do not have significant penetration in the industry, and that's really not surprising. A decade sounds like a long time, but especially having a strategy of staying small scale, which is the direction that I've gone, it's really not that long to develop technologies that are going to have a significant impact and going to be accepted into an ecosystem that is so large.
You're more hopeful that the advancement is pretty soon in this field as well.
I am confident. This field, part of the reason I left is this field has been doing things the same way for the past decade, even before I entered. It's based on register transfer language as the accepted way of doing silicon design, doing a semiconductor design. And it's a different world than the world that RTL was born into. The problems are very different. And we're kind of at this breaking point. I would say we're well beyond the breaking point where an RTL-based methodology can carry us forward. And the industry is coming to a level of agreement, right? There were many folks in the industry sort of independently realizing and feeling like this is not the way we should be going forward. Now I sense more consensus.
More collaborations?
Not so much the collaborations specifically, but just the agreement and the understand. I don't have to spend as much time convincing people that the industry's broken.
They're ready to try and dive in.
Now the question is, what is the right way forward for the industry?
Yeah, especially seeing the growth of NVIDIA, we can say that more companies are now interested and encouraged to dive into AI space.
Yeah, definitely with AI, AI changes the game completely for everybody. It doesn't matter what business you're in. And so the question is, how is it going to change things, not if it's going to change things. And what does that mean for the industry? And that sets up the industry with this mentality that things are going to change, and let's figure out how.
So you have been in the space of design verification of silicon for about like a decade, 18 years or so. So how do you feel seeing the 700x in terms of the number of transistors now, the technology that has changed?
Over the course of my career.
Over the course, yeah.
Yeah, I mean, the technology scaling, this relentless Moore's law, pushing us smaller and smaller.
Yeah.
I mentioned the rules have changed, and it's not the world that RTL was born into, right? And it's all because of scale, right? For example, RTL was solving problems of being able to model a circuit that you have in mind. When you started a project, you had a clean slate, and you coded RTL to describe the behavior that you want to implement.
Right.
And then next project comes along, and you throw that RTL away, you start again. That's not how we do design anymore. No one's going to write 100 million lines of code from scratch for the next chip.
Right.
It's all leverage and reuse. So what are the mechanisms and the methodologies that need to be in place and the tooling to support that vastly different methodology and different set of problems?
As we all know that Moore's law also has a breakpoint now. It has reached a breakpoint.
Well, you say we all know it. I don't know it. It all depends on your interpretation of Moore's law, right?
So you still have a hope for it?
Well, the thing that is absolutely clear is technology will continue to scale.
Do you see AI is going to contribute into that scaling?
Absolutely. I mean, AI plays a part of everything, and it's a question of how we use it. And I think I can't claim that I had a brilliant vision for AI coming along and how that would affect the world, but perhaps more by luck, I think the technology that I have is an important technology for cracking some of the challenges that the industry has in adopting AI, applying AI to circuit design. The biggest challenge with circuit design, as you know, as a verification engineer, is verification. And AI can create bugs for us very quickly.
Definitely.
It's very good at that.
Too helpful.
So, how do we let this technology that can, is almost creative, it's kind of the surprise of AI, apply to this domain where we can't accept a 0.00001% failure rate, right? How do we make this technology that is fundamentally imprecise precise?
Yeah, that's important. So now a little bit about your company. How does TL-VERILOG differ from traditional methods, and what challenges did you face when introducing it?
Right, so TL-VERILOG is the sort of the embodiment of the methodology that I think is going to be important to carry us forward. Unfortunately, new methodology in this case requires new language. New language is a huge barrier, so I'm not going about it as language from scratch. It's one of the things that makes it unique. It has to work with the existing ecosystem. So I'll be blunt, there's absolutely nothing that I care to preserve about Verilog as the predominant language for capturing RTL, expressing circuits. But we're not just going to throw it away and start from scratch. Yeah. So TL-VERILOG is a strategy for incrementally transitioning us from where we are today to where we need to be. And so the incremental nature of it is one of the characteristics. You know, on the fundamentals level, what transaction level Verilog is about abstraction. Productivity is always about abstraction. If you're going to be more productive, you just can't manage the same amount of detail. So how do you do that? Hardware design is kind of unique because we care about the gory details. And on modern silicon, there are a lot of gory details. So how do we manage all of that gory detail in a more productive way? So abstracting in this domain is very difficult because we don't want to give up that control. And that's what TL-VERILOG is fundamentally about and what makes it unique from other design methodologies. It's not let's define a new abstraction level and figure out how to design there. It's how do we manage this hierarchy of design abstraction. You know, how do we bridge the gap between this layer of abstraction in the design process and the next layer down? And how do we do that in a way that's provably correct? And, you know, and those modeling at different levels of abstraction is linked and everything is connected. How do we share code across levels of abstraction? Things like that.
Okay. So next question. Makerchip is a fascinating platform. What was the vision behind its development and how has it been received by the community?
Well, the vision behind Makerchip, I suppose, is pretty simple. I found myself building a business around design methodology, which required new language features, and you can't form a business without an elevator pitch. How am I? No one is interested in an elevator pitch about language features. So there's got to be something more, you know, more visual to talk about.
You're right.
I mean, that's one side of the story. It is important, of course, to have a platform, right? Language is not everything. This story is about productivity, and productivity means language features. It means environment, tools, ecosystem support, all these, you know, all these things. And so Makerchip is the IDE that supports transaction level Verilog and the methodology behind it. It's been, you know, and the push for Redwood is to kind of sell this story about design methodology. This is what you know, this is what is new for the industry. And folks need to be convinced of that. What they don't need to be convinced about is that being able to design from your web browser without downloading 100 gigabyte software bundle and in most cases paying very high license fees and whatnot. Being able to access all of that through your web browser. Being able to conduct a workshop without installation requirements and platform issues and these kinds of things. That's an obvious win, especially in education.
Yeah, especially in education. Yeah, that was I was focusing on. So it's like open source hardware you're talking about, right? So what do you think about them? Like you have already in support of that, obviously, with your statements. But how do you think it is going to impact, you know, the educational journey of a person also, and also how is it going to help the, you know, companies?
Right. Yeah. I mean, there's a lot of questions around how does open source work in a commercial setting? What is the role of open source in that ecosystem? The open source community tends to be very, I don't know the right word without sleep, but you know, just very passionate about open source and everything should be open source. And, closed source is always an obstacle and, you know, we just can't accept that. So, you know, big push now to create a complete EDA flow. I mean, that's a milestone that the community has passed at this point, and a very exciting one. And entire tape outs based on open source silicon, open source tools. That's very exciting. My approach and sort of finding the right balance between openness and enablement of the community versus, you know, it's very difficult to have a business model around open source. So how do you create that business model? So my philosophy is the leading edge of everything that I do is closed source. So I can have a commercial business model and support the advancement of the technology. And then after a certain amount of time, once there's a new forefront with something new value to offer,
Mm-hmm.
the previous wave becomes open, enables the community. Right. The community can rally around it.
Innovate over that. Yeah.
Exactly. And so this is a commercially viable route to enable the community with open source. It's very difficult to perpetuate an open source contribution to the community if there's no business model behind it to support it.
Right.
And so, yes, my forefront is proprietary. That's important to the open source community because that's enabling the continuation of development that is open.
Right. So another innovation of yours, the Warp V code generator. Can you share how it has influenced open source hardware development?
Sure. You know, RISC-V is sort of this rally cry for the open source community lately because of the philosophy that they've taken, the openness that they've taken with the core. Or not the core, the ecosystem, the instruction set architecture. I think everybody who's doing something similar to me of innovating in an EDA space, innovating with design language and methodology, has done the same thing. We appreciate the rally cry around RISC-V and use that as a demonstration vehicle to, you know, embrace the community around our technology. So Warp 5 for me is kind of two things. It's a way for me to like eat my own dog food, if you will, use my own technology, push the limits of what the technology can do, explore what it can do, help to define new features and new capabilities. So that's, you know, that's the value for me. And then, you know, being able to offer that to the community to rally around. Many of the students that I work with. I have a long list of projects that I believe are extremely exciting projects that I'm happy to collaborate with folks openly as open source projects. Warp 5, the Warp 5 CPU core is one of them. I think it's probably the least interesting in my list, but it's the one that gets the most attention because it's RISC-V. So it's sort of that rally cry.
Then what do you think is the most interesting one?
Oh, the most interesting project on my list. Well, I guess I should have prepared for that question. So the most, no, it's a good question. So I guess one of the projects on the list that I find exciting is there are a lot of FPGA boards sitting on shelves, right? I've got probably 6 FPGA boards sitting on my shelf that I haven't even taken out of their package yet. That's a lot of computing power that's just sitting idle. With modern technologies, we can connect those FPGA boards in the cloud. So I'm interested in seeing an ecosystem, a platform where individuals can share their FPGA boards and have easy access to FPGAs, where you can just jump on and say, I need this FPGA, let me experiment with this.
Interesting.
Let me grab this and play around with it and give it back. I've done actually, you know, sort of leading up to that idea, I've done several projects based on cloud FPGAs when Amazon started putting the FPGAs in their ecosystem. You know, it's generally a domain I think there's a lot of exciting opportunities for cloud use of reconfigurable hardware.
Right. So what are some of the most pressing challenges facing the silicon in our design industry as of now? Pressing challenges.
Well, that's a big question.
Something that comes across, the first thing that comes across your mind.
First thing that comes across my mind. Well, I think many people today would answer security. That's a big challenge and it's getting a lot of focus.
Security then?
Well, that's the easy answer, so maybe I'll stick with that one.
Okay, so we'll move on to the next question. The industry has seen incremental tool improvements. Why do you think a more revolutionary change has been slow to occur?
Yeah, I mean, revolution is hard. And as I said, the industry is very deep at this point. It's a complex ecosystem, so it's hard to do those revolutionary changes that requires a complete overhaul in a very complex environment, complex ecosystem. And so, yes, the strange thing, I always find this strange, is that large companies have this tendency to become set in their ways, right? They've got their cash cow, they've got their business model that works, and they'll keep pushing on that as long as it's successful for them. And that kind of holds them back to do the innovations that are necessary to carry them forward. You know, it creates the sort of Titanic that Eventually, the ecosystem gets to the point, the industry gets to the point where they need that revolution, which is where we are today. But it's very hard for, the world is not companies. A company is not a thing. A company is a collection of people. And people make choices that make sense to them. And it's very hard for any one individual to be in a position to say, well, yeah, to take that risk, to make the change. You know, no good deed goes unpunished. So the motivation's just not there for the revolutionary change.
Okay, so we are doing a deep dive into technical aspects of the Redwood. So we have this visual debug from your patent portfolio. It stands out. How does it transform debugging in circuit designs?
Yeah, I guess the industry, and I've even had conversations with Synopsys execs about this, has viewed EDA as providing the ways that engineers should do their work, the ways that engineers should do debug, and the debug tools that the industry's been providing have ways of generating visual representations of the hardware that designers are designing, what's happening in the RTL. Oh, this is a state machine. Let's give you a state machine view of what's happening. The reality is every circuit by nature is different. As designers, we all have pictures in our head of what it is we're implementing. And then we codify it, capture it in code, and then we give it off to the tools so the tools can interpret what we've done and represent it in a way that's helpful to us in the debug process, helpful to us to convey what we've done to others in the design team. Visual debug puts the designer in control of the representation of that hardware behavior. So just to be clear, visual debug is a feature that allows you to define the visual representation of your circuit and see it animate in simulation. So rather than viewing a waveform viewer that's this just mountain of data, you can organize that data in a way that's easy to comprehend visually. And so visual debug puts the designer in control to help them
analyze the situation more efficiently.
Yeah, and it's a tool to help the designer, him or herself, as well as to convey information to the rest of the team about the work that they've done. It's a form of live documentation, right? Documentation, the biggest problem with documentation is that it's often wrong. It becomes stale. So what's the good of documentation if you can't trust the documentation? Well, the visual debug is tied to the actual hardware model. It's correct.
Okay. So Steve, how has your leadership style evolved from your days at Intel to founding Redwood EDA?
I think many people you could ask what my leadership, or ask that question to, and they'll say, Steve's leadership style? I don't know that he has a leadership style. How has it evolved since Intel? I mean, I think I have always tried to pull people together and inspire people to do work, not tell people the work to do. So I think one aspect of my leadership style, there's always a pile of work to do. Some of that work is extremely exciting, but there's always the grunt work that just needs to get done. And I think most leaders will look across the skill set in their team and they'll say, we have the junior engineers, we have the senior engineers, we have the engineers with all the experience who, obviously they're the ones making the decisions and steering the ship. And the more challenging problems, the more exciting problems, the more cutting edge, innovative problems tend to get given to the more advanced engineers. And the junior engineers get the grunt work. That's not very motivating to enter in and be a part of the ecosystem. I tend to take the grunt work tasks myself so that the exciting activities can be taken on by the junior engineers and they can be inspired by that while, watching over their shoulder, coaching, giving them direction, making sure it's going in the right path.
It's the best way of learning, actually.
Yeah, and along those lines, I really enjoy being a mentor in a program called Google Summer of Code. That's been a great way to engage with students and get students inspired. The projects that I mentioned that I keep a list, the students get very inspired and excited about those projects.
Yeah. All right. So if you could go back to the beginning of your career, what advice would you give to your younger self?
To my younger self.
Yeah, that is going to be very helpful for people like us just starting our career.
Yeah, you're good with the big questions, I guess. I guess I would say one thing is to ask a lot of questions. I don't know. I think that's something Indians understand more than Americans, if I can generalize.
Okay.
But yeah, asking questions is just so important. That's how you learn. And people say there are no such thing as dumb questions. There absolutely are such thing as dumb questions. I'm
Yeah,
sorry.
I'm terrified of those.
I'm sorry. You can make a fool of yourself by asking
Yeah.
questions, but it's way better to put yourself out there and make a fool of yourself and work past your ignorance
Right.
and get yourself to a better point. And people recognize that and appreciate it.
So, and what drives you to stay motivated in such a complex and demanding field? Still motivated to get up every day?
Well, that's why I walked out the door, right? Is when I realized I wasn't motivated. And so being able to chart my own course and innovate freely.
Yeah, starting your own
I think that's
company.
important.
So, beyond technology, how do you envision Redwood EDA contributing to the society?
Well, I guess technology is part of it. I mean, honestly, I often ask myself whether I'm doing good by introducing more advanced technology to the world, right? Any technology can be used for good, it can be used for harm. I mean, what's the harm of better circuit design methodology? It's not as obvious as nuclear power or AI. What's the value of advancing society? There are a lot of downsides in general of advancing society. It creates a more complex society, and many problems actually arise from that. But to me, it's maybe more about making the work, day-to-day work, more fun. I mean, I feel that myself. Obviously, I'm very attached to the technology, so it's a little bit different for me. But I felt like designing circuits was kind of painful and a fight with the tools. Now, using my own tools, I feel that the tools are doing what I want them to do and working with me and helping me to do the things that I'm trying to do.
It's not that tiring now. It's more efficient, and we can, progress on
And
projects
it's about
way
that
faster.
feeling of just enjoying the work.
Enjoying the work, right, right. How do you see AI and machine learning shaping the future of silicon design?
Yeah, another big question. You're good at these. So it's obviously going to have a huge impact. And we talked about earlier that it's challenging to apply AI in a space that needs to be so precise. But there are definitely ways AI can contribute. Certainly early on, there's a lot more opportunity for applying AI in the verification space, I would say, than the design space. But I definitely see a lot of opportunities in the design space longer term. The early impact, I would say, of AI is to make us more productive, to accelerate the process.
Yeah.
Accelerating the process, making the turnaround to new silicon faster and more nimble. That's the challenge that we're facing. And AI works very quickly. So to the extent that we can apply it and use it to accelerate the process.
So have you incorporated AI machine learning in Redwood EDA?
Work in progress. It's not incorporated into any of our current commercial offerings, but it is, of course, a lot of the focus of development.
Okay.
Yeah. So maybe one thing I'll point out in particular, current focus with AI is code conversion. So I've been kind of struggling with this challenge of what is the right direction to get the industry from where we are with Verilog. As I said, everything is leveraged today, so everybody is leveraging Verilog. That's what we have to work with. How do we translate that and automate the process of translating that into transaction level Verilog to take advantage of the constructs, to make our silicon designs more robust, reduce bugs, reduce maintenance. And it's very difficult to convert code without making the code look like it's machine generated and very unmaintainable and lose comments and that sort of thing. And AI pops up on the scene and becomes more capable. It's the perfect tool to do that and preserve the meaning. So the challenge for me right now is AI models don't have any clue about TL-VERILOG right now. They'll give you an answer and tell you what TL-VERILOG is about, and it'll sound good, but
how to use it, they don't know.
Right. And so that's where the focus is teaching AI what TL-VERILOG is all about, providing that training data. And right now the focus is implementing that conversion. I mean, if we can take the world's billions of lines of Verilog and just magically turn them into half as much code that needs to be maintained through AI automation, that's a very immediate impact to the ecosystem.
Okay, so as we are closing in on our podcast, we have some light-hearted questions. So if you weren't working in the silicon design, what field might you have pursued and why?
Honestly, I think probably most of the people watching the podcast, listening to the podcast, are probably in the same camp.
Yeah.
We're just built as engineers, I think, and it was always sort of in my blood. I don't think I knew what the term engineer meant until very late in high school, but that's who I was. And
Okay, always destined.
I think so, one way or another. I mean, not necessarily electrical engineering. So, the one thing I can say is mechanical engineering, say, sort of had a knack toward mechanical engineering, just came very natural to me. What led me to electrical was, and computer engineering, was just the realization that, whatever discipline I choose of engineering, my day-to-day job is going to be working with computers, programming computers, and I don't want to do that job without understanding computers. And so that's where I focused, and that's,
Electrical engineering then.
Yeah.
Okay. What's a little known fact about you that might surprise our audience? Any fact?
What's a little known fact about me? I'm pretty transparent and unremarkable. I cut my own hair.
Oh.
Maybe that's obvious to everyone looking at me. Maybe not. I don't know. But that's just something. My brother cut his own hair, and I just.
That's a good skill to have. Yeah, really. Okay, so if you could design a dream chip without any limitation, what would it be? And what would it do?
So many exciting architectures to be explored. I mean, I think that the time that we're in right now is an extremely exciting time to be in this industry. There's so many opportunities for new architectures, so much. We've sort of gotten to this scale of parallelism, the need for parallelism, and that opens up the need for creative new architectures to address problems, application-specific architectures. David Patterson, I guess, has the term golden age of computer architecture, right? The bulk of my career was CPUs. It was all about CPUs. CPUs were compute. And then we kind of reached this level of parallelism that opened up the doors. And so I think there's a lot more opportunity to explore. So I'm avoiding your question. There are many different types of architectures that are relevant now and interesting. All right, I'll try to give you a specific answer. And this is just one little idea that I had, I don't know, 20 years ago that I thought would be fun to implement, and never, had the drive to do it. And I'll share it with everybody. Somebody can take my idea and run with it. So the idea is that probably most folks have seen Conway's Game of Life. So it's just this very simple set of rules that defines the behavior of a system. And so I always thought it would be fun to sort of take that to the next level, define a more interesting set of rules, but still a very simple set of rules. Implement that in hardware, replicate it out, just let the hardware run, let sort of life evolve, right? And just play with it, right? It's a pet rock, it's a toy, but this little circuit on say a card with some visual display that you can see, and maybe your little card can plug into somebody else's card. So you have your little culture growing, and they've got their culture growing, and you can plug them together and let worlds collide and see what happens. It just seemed like a
interesting,
fun little thing to do, right?
Yeah. True. So the question from one of our audiences, for all the students basically in the educational fields in India, also in abroad, all these open source hardwares, makership, and all these are going to be really beneficial for them in the learning process. How do you feel about that? How is it going to be included in the academic? How do you approach, you preach for that basically? How do you see it?
Right. Yeah, so it's been, I guess coming from the world that I'm delivering into of semiconductor design, I knew all of the challenges that I would face of adoption of new methodology into that ecosystem. It's always been my plan to focus more on academia, on the open source community, to evolve and grow the technology and mature the technology before putting the bulk of my focus on industry. So the learning curve for me has been more about how resistant academia is to new things. I'd like to think academia is this fun playground that's all about innovation and technical merits versus commercial applications.
I think it's very rigid. Like they have a strict curriculum, they have to follow strict subject lines, and there's
Right.
no experimentation as what we have experienced.
That's exactly it. That's been the surprise to me, and there are many reasons for that. One of them being job posts are looking for system Verilog, and educators feel like that's the skill that they need to provide the students with so that they are in a position for a job. One of the things that I think is important to realize is that if you are going through school and getting an education that teaches you existing industry practices, old school thought process, system Verilog coding, right? First of all, it shouldn't be about the coding skills. It should be about the understanding. But, if you're coming out with system Verilog skills, you're positioning yourself as the low-cost alternative to the more experienced engineers who have that skill. There are plenty of Verilog coders out there. So if that's what you're looking for, if you're looking for a path into the industry so that you can get a job in the industry, that's fine. That may be appropriate for you. But if you're the type of student that's looking for the jobs where you can differentiate yourself, those are the students that should be given the opportunity to explore new technologies and position themselves as, hey, we're the next wave here. We're going to bring something new. We're going to deliver into the next generation industry, not the previous generation industry. And, that's always a discussion with professors who have their sort of set curriculum and their set way of doing things. Why should they step back and innovate curriculum? Why should they develop skills amongst their students that the industry is not currently begging for, right? But I think it's not the right mindset. The world changes. You have to expect change. You have to be a part of change.
And I think it's something that the students should also be pushing from their side.
And I do see that quite a bit, actually. I see less. The professors that I talk with often believe that their students want the Verilog skill set because that's what they hear about. But talking with the students, it's a mix, but I would say the majority of students is much more excited about the new technologies than the existing technologies. And they see MakerChip and get to play around with it and, get to see that 5 minutes into the first lecture on circuits, they can be playing with circuits and seeing what they do, seeing their behavior. They get very excited about that, and they're much more interested in learning the new technologies.
And so we have reached the end of our podcast. Thank you so much for coming here. It was really interesting and insightful talking to you.
Thank you, Apurva.
We'll see you for another podcast on VLSI for All.